Alrighty. Okay, so your lab number 2 has been released. Make sure you work on that. And the due date is actually next week. All right, please check the exact time for the due dates. And tomorrow, during the scheduled live session, the TA will be there. And myself, I will be in my office, but you can feel free to drop by my office if you got any question during that hour, right? It's reserved only for you guys. You just feel free to come. If you have the need, just come. And for your lab number 1 solution, I would like to just dive a little bit deeper again. I do have a few more things to say, just to make sure you guys can look at that independently, right? Once we have got all the highlights, we'll finish that. And today, and then we're going to do that extra exercises on math review. I got nested quantification and some interesting questions for us to solve together, right? And then we can finish the math review, and we might be able to touch upon very briefly about the model checking lecture. It's going to be a brand new lecture, which is going to last us beyond the reading week. We're going to talk about some new logic, but we're going to start with some introduction slides as ever, right? Just to set the context. And office hour as ever, right? Just drop by whenever you find the need. Any question about the course in general? All right, that's good. Okay, as usual, let's do a quick recap about last lecture. So last lecture, we basically talk about these 3 things you really want to watch out for your lab number 1 solution. Of course, these are the trickier concepts which I'm going to talk about in class, but there will be other things you also got to go over the solution of lab 1 to explore yourself, right? That's something I'm going to rely on you, and then we'll, of course, assume that you have gone over the solution very carefully before the test. So let's now see what we spoke about last time. As for the finite reachability graph, it is very important for you to note, whenever we say finite reachability graph, what we say finite over here is really about a finite number of states in the graph, right? If you talk about 31-on-1 context, you know, for each graph, you got nodes, you got edges. So we're saying the number of nodes in your reachability graph must be finite. It cannot be infinite. If there's infinite, there's no way for the traversal or that first search to ever terminate. And the way to really make the finite reachability graph happen, even though we got unbounded, like a while true event interleaving, is by having finite number of nodes in the graph, but we do have some cycles over there. So the cycles there make sure we got an infinite number of paths that can happen, right? So you want to really distinguish between when we say infinite number of states versus infinite number of paths. They really talk about something very different, right? You want to make sure you understand that. So that's really about the first point, and we also dive very deep into it. I'll give you a few more recaps once we get there. And we'll also talk about using labels to kind of specify whether you want your updates to be atomic or non-atomic. I'm going to show you a little bit more today about the state graph you can generate from TLA Plus, and also highlight certain parts too, so you can also dive deeper into it by yourself. And also we're going to talk about the variance, right? So this will be the part I will also require you guys to know, right? So about how to encode the variance. I'll give you a little bit background, and then maybe beyond today, maybe tomorrow, early Friday, I'm going to include some links for you to catch up about the idea of variance. I'll give you some summary anyway today, right? So just in case you find the extra need. So you will be expected to know about the variance, okay? I'll talk about it later today. All right, so the first point about finite reachability graph, so you can refer to the detail in the recording, but we got this conceptual sketch about the finite number of nodes, and also we kind of see the corresponding state graph, right? You guys can take a look, okay? When D is equal to 2. And of course, I kind of show you the statistics from the checker. As we try to double the size of the D, about the maximum number of cars allowed in the system, then the number of states will just also double in a linear fashion, which is not too bad for this particular example. But for state explosion problem, we also got to watch out for that. Sometimes the growth can be exponential as opposed to just linear, right? We're going to watch out for that. All right, so this is more like a general advice. So whenever you got TLC checker to help you, if you really try to develop your system and also write some properties, if the TLC checker says, yes, everything checks, that's definitely a good sign. But I would say always just to be sure. Sometimes you can get some false how to say, like a false result as to whether your system is correct or not. So you really want to maybe set some very small value constant and generate a state graph accordingly and go over the graph yourself just to make sure the evolution of the transition is really what you expect to have. Okay? So this is really about the first point. On the other hand, if you actually got some no answer from the checker, of course, you have no choice. You have to somehow look at the error trace alongside with the state graph generated to really find out what's wrong with your model. And then you want to fix your model accordingly. That would be something you may be expected to do in your assignments and also your programming test. Okay? So that's just a general guidance about the big picture. And so that's the second highlights, the second aspects, which kind of started halfway. So we talk about if you got, for example, 2 labels over here versus 1 label, right? So again, don't really get confused with what we saw in another tool called Rodent, right? We don't really use Rodent anymore in this course. You're going to stick to what's really set there for you for TLA Plus, which is another tool, independent. So here's the principle. Whenever you got, let's say, multiple actions here, okay, multiple actions over here, it depends on what your need is. If there is a requirement that these multiple updates must be executed atomically. Atomically means there should be no way for you to inspect what's really happening in the intermediate states. If that's the case, you should really try to put them in under a single label. But if somehow there's no such a concern to really observe the intermediate state, sometimes it might be the case. In that case, you may want to use multiple labels. But in our scenario for the bridge controller, these 2 updates about updating the N and updating A, they must be done atomically because we got the associated invariant A plus B plus C equals N. Somehow, let's say currently 0, 0, 0, and 0, let's say, right? So now we're consistent. However, if you say I want to update N in the abstract action from 0 to 1, now if I only stop here and see the intermediate state, you can see some inconsistency because 0, 0, 0, and 1, they are not equal anymore. So what we really want to do is to make sure A over here is also updated atomically at the same time. So that's why these 2 updates cannot be done using 2 different labels. They must be done under a single label. Right? That's really something you want to see the difference. And of course, in the test, you want to really judge the scenario which one it should be. I shouldn't really say always you should use a single label or always you should use multiple labels. As I said, you have to decide the scenario. But for the bridge controller, we want the invariance to be satisfied. At any intermediate stage, it might be violated. We don't want to see that. So that's why the multiple updates should be done atomically. All right? So that's really the principle you want to grasp from this lab, which is very important. Okay? And I want to, okay, I think that's pretty much the end of Tuesday's lecture. Any question?
So the first execution is not atomic and the second one is atomic?
Correct. So the first one there in red over there, you can see in these 2 versions here, we got the same 2 updates, right? You can see the 2 updates are about N and A, and also N and A. So the first one here, we got 2 labels. And each label you can think about will be a value for the program counter. Each distinct value for the program counter is going to result in a new independent state, which we'll see in the state graph. Okay? So that means you're going to have one state with this being the PC value. You're going to have a second state, separate states, which will have its PC value as this value. So you got 2 independent states. But the problem is if you got independent state, let's say this. Okay? You got abstract, you got concrete. But after you have done the abstract updates right here, in which case you have only updated N. You haven't updated A accordingly just yet. So at this point, the tool is going to say, oh, no, 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 you haven't updated A at the end of this state. It's too late. So you got violation, which I'm going to show to you in the state graph. On the other hand, this one here is going to make sure all the updates will be done in a single transition. For example, once we have done a single transition, this resulting state here is going to have both N and A updated simultaneously. That's also something we can observe. Okay? The principle is you have to see which one is appropriate for your particular verification context, right? And then decide which one to use. Okay. All right, any other questions from last time? Subtle but important, right? You can see there are many subtleties there in the lab number 1 that we should really be aware, right? I think it's a good lab, right? To really not only to show to you how to use the tool, but also to be aware of certain verification issues, depending on what you need. All right, if no further question, let's move on. I still want to continue with this particular aspect over here, but instead I'm going to dive a little bit more into the TLA plus tool, so you can also try to reproduce what I'm trying to do here. All right, so let's now just review. Let's just kind of bring us up to speed about where we were last time about the tool. All right, so the solution module I'm looking at is something called Bridge Controller N1, no variance, right? Let me just show to you very quickly, right? So to really reproduce what I'm doing here, you want to look at this module over here. Bridge Controller, we're doing M1. So M1 actually involves N, A, B, and C, right? And then the no variant version. We'll look at the variant version when we talk about variance, okay? No variant version. Look at that one, and if I just remind you very quickly, in the solution module, if you open that, give me one moment. There we go. This one. All right. If you open that, the one there, which I opened on Tuesday actually, that one will be only a single label. But on Tuesday, I kind of changed that to be the 2 label version, right? Okay, let me just remind you. If I got the 2 labels over here, and then I will create a model accordingly. For simplicity, let's say the D is set to 1, just for simplicity, right? So we can allow only 1 car in the island maximum, okay? That'll just make the resulting state graph a little bit smaller for us to explore further. Right, if you click on the model there, and then, okay, let me just close that. And then if I say I want to check it, all right, you will see some error trace over here. Let me bring to attention to several things. So number one, you can see about the number of states that's being checked. You can see distinct states over here, right? That's what I showed you guys last time, right? About how many states were explored. 9 states, not bad at all, okay? So that's really something manageable to be inspected by us quickly. And then you can see something right here. It's a little bit small font size, but you can see under model 1D1. So this is something about invariant 1_4 is violated. So this one is telling you the error trace that's shown below is showing to you how you can go from the initial action, initialization, all the way to the first stage where that particular invariant was violated, right? That's how the error trace should be interpreted, right? I'm going to show you on the iPad and give you a little more close up to see. Anyway, so that's something you should really try to reproduce, and feel free to also explore a bit about the error trace itself, right? That's something I will expect you to do on your own. But let's take a look at this here, all right? Okay, so this is the one that's failing, okay? This is one. And let's see right here, right? I'll go right to the point. So if you recall in the module here, okay, let me just show you what I want to show you directly. We are talking about ML out. And then somehow we got 2 labels. So the first one that's going to be executed will be the abstract one, which will update N only. All right, so let's see where we can see that. All right, so if you look at the diagram here, you will see that I already highlighted ML out action abstract. So this one here is supposed to change the N value. At the moment in the pre-states, it's actually 0, right? So you can think about this one is telling you the following. Let's just visualize that very quickly, okay? So this one is telling you I have the pre-states over here where PC is equal to the ML out action abstract, right? So that's a pre-state I have. And then what I will expect to see will be once the transition actually happen, right? The transition, what I'm talking about is over here, right? The transition, once it happens, is going to lead me to a post states where the effects is actually going to happen. If you look at the module here, the effects is going to be N will become N plus 1, right? So you can see after that, you will see in the resulting states, N has become just 1. Over here, right? That's something you want to write to see that right away. And in that post states, we'll get PC equals, over here, you will see it's ML out action concrete. Okay, I'll just write it down and then I'll clarify some stuff here. ML out action and then concrete. Okay, what does that mean? This is how you should think of it. Let me just copy down the code from there. So in the code, you can see we got ML out action abstract. And then here, there's a label and we say n becomes n plus 1. Also, we got ML out, action, concrete. That one we got A becomes A plus 1, right? I'm just copying what we did in the module. So you can think about here. This particular states, I'll put it 1, is exactly at the point that we only talk about the label over here. So this is right before the action takes place, right before that, all right? And then this arrow over here represents the action that's going to be executed right here, number 2. And then the resulting state, number 3 over here, is basically right around this label over here. So that's why you see the MLL action concrete over here. So this state here is right before we are trying to do this particular updates, right? So it's important for you to interpret the PC counter and also the state appropriately. One thing you can notice right away, in the state graph, we don't really see any transition that's actually going to do A becomes A plus 1 to fix the invariant. Nothing. Simply because at this stage already, after updating the n, this state here already creates some inconsistency about the invariant. So that's why the model checker, TLC checker, is going to stop there and generate error trace right away. Right? It's a very important thing for you to note. Right? I'm going to write it down. So it is very important for you to realize the following. So I'll just draw some boundary over here and then remind you. Okay? Okay, I'll put it there. So basically, for this one here, sorry, it's a little low here. Okay, I'm going to write there. So the post states of ML out action concrete is not shown because invariant 1,4, which is the one that's being violated, you will see invariant 1,4 violated in the tool, right over here, is already violated. Right? This is a very important point for you to see. Otherwise, you might be thinking, well, I thought the concrete one is just going to make sure the invariant will be maintained. Not really. They have to be executed atomically in this case, rather than one after another one. Okay? Because it's already violated. All right? And let me just do a little bit more stuff over here. Okay? I want to make a little more annotation here. So think about this state over here is the pre-states of the abstract action. And this one here is the post-states of the abstract action, the same action, right? Right after n has been updated. At the same time, this is also the pre-states of the concrete action. Okay, so here I really meant to say abstract, right? All right, I may annotate that on the graph, and then we're done with this one here. And then I will try to fix the error and then show you the correct version and explore the state graph, and then we are done with this aspect. So what I'm saying here is this particular state is really the pre-states of the abstract action, because afterwards you can see the n value would be changed from 0 to 1. And this over here is the post states of that abstract action. At the same time, this one here is also the pre-states of the concrete action, which will never occur because the invariant has been violated already. Okay? The pre-states of the concrete action, right? So again, we are trying to have some conceptual sketch, which is very useful, and try to see the correspondence in the actual state graph accordingly, right? It's also very important thing for you to actually have whenever you want to explore the state graph. All right, any question here about what we are doing here about the state graph? All right, explore deeper about the state graph. I think it's very useful information to really see what's going on over here. Okay. So what I would do is, let me just go back to the model there, module. Let me close this, and then let me fix the issue here. And then we'll see one more time the state graph, right? Now I'm trying to do a single label. Okay, sorry, I did a wrong fix. Let me do it again. Beg your pardon. There we go. Let me undo it. Okay. I'm just going to delete the label. That's what I meant to do. Right? And then, rather than abstract, let me fix that to be just a single action. A single action is going to execute 2 updates atomically. There we go. Okay, save it. And because we are modifying the algorithm, so we should make sure we remember to translate. So I'm going to say translate. Okay, all good. And then I'm going to go back to the model and try that again. All right, you can see, right? Now a single label with the 2 actions, so now everything verifies, which is good. And what I need to do to finish off is to show to you the actual state graph and point out to you several important stuff. All right, so this is the actual graph that's generated. Okay, several things over here. Okay. And let's now do the conceptual sketch very quickly to see how we are supposed to understand this. And just again, we are having So this is the correct version, right? What I just did. Well, again, no abstract, of course. I should really delete that. Okay, just action. Just that. Okay, and then I want you to look at maybe here. So this diagram here kind of nicely talk about the sequence of events that's going to happen. Okay? So here we're making the assumption that the maximum number of cars that can be in the island will just be 1. So we're talking about D is equal to 1. All right here. Okay? And then you can see the number of cars in the island will just be N. Sorry, the number of cars that will be outside the mainland will just be N. Okay? So think about what's going to happen here. Okay, I'm just going to write out all the variables and do a little bit of conceptual simulation before I show you the state graph. Otherwise, you might just get lost. In the beginning, we simply got 0 and then 0, 0, 0. Right? Just to remind you, A will be the number of cars on the bridge heading to the island. B will be the number of cars in the island. C will be the number of cars on the bridge heading back to the mainland. Right? And N here will be all the cars that will be on this particular compound. Anything that's outside the mainland, how about that? It will be the number of cars. Okay? So that's why we said N should be equal to A plus B plus C. In the beginning, 0 equals 0 plus 0 plus 0, which is good. Okay? What's going to happen is this. The graph is going to show. Let's say we got the first event, ML out. Sorry, just give me one moment. There we go. All right, so by the way, we don't really have traffic lights in our model just yet. So you don't need to worry about traffic light. Let me just cross it out. All right, let's see the sequence of events that's going to happen. So what we have is, first of all, we're going to have ML out. Right, the ML out here is going to decrement, it's going to increment N. So now let me say this is number 1. So number 1 is actually going to increment this from 0 to 1. All right. As soon as this happened, you can see N has already reached the maximum for D. From this point onwards, ML out will be disabled until some other events to fix it. All right? So you want to say, so after this point, after occurrence of ML out, it is disabled until N is decremented, because we only allow maximum 1 car outside the mainland. But now in this case, we already reached the maximum. So only after n was decremented back to 0 will that be enabled again. And what about the other events that's going to happen, which will also be shown in the state graph? Let me lay out that to you. So there is another event called ILN. ILN. All right? So ILN, oh, by the way, ML out over here is also going to increment the A by 1. All right? Over here. So this is also what one would do. It's going to do two things, right? Remember atomic optics, right? And then we also got another event called ILN, meaning that the car is going to go into the island. All right, so for that one there, it's going to increment B and decrement A. So let me call it 2. It's going to decrements and then increments, right? So this will be number 2. But the invariant is still maintained, right? And the car, the single car there, stay in the island for some time, and then it's going to go out of the island at some point. So let's use another color here. This will be number 3. So number 3 will be IL out. That one there is going to decrement B and increment C. So 0 and 1, right? That's number 3. All right? And finally, we got the events that is going to restore the guard of ML out. That'll be the final one. So that one there, I'm going to use one more here. So now this will be number 4. Number 4 here is called ML in. Go back in the island. Go back in the mainland. So this one here, let me call it number 4. So number 4 here is going to decrement C over here, and also decrement N. Right, that's number 4. So once number 4 is done, you can see now N is now again strictly less than the maximum. So now ML is enabled again. Right? So this is a very important relationship that's encoded in the model that you want to be aware. And let's see how this one here is reflected in our state graph. But just before that, let me just do one more. Okay? Important for you to see this visual here to see how things are going to happen. At the same time, I'm just going to sketch out one more graph. Okay? So think about what's happening here is we got the initial configuration. So we got D, which is maximum 1. And we got A, B, and C. They're all 0. All right? And then after that ML out, we simply got A would be equal to 1. Oh, I forgot the N. Okay, I'll put N equal to 0 here. So N will be 1, B, and then C, right? So at this point over here, ML out is simply disabled. Well, it's simply that, right? And then what we expect to see will be another 3 events happen. So we got the IL in, and then we got the IL out, and then also we got MLN. MLN is going to bring us back to right here. Right, for the exact state value over here, that's already mentioned over here, so you can check. All right, you can also check on the actual state graph. But the point is, after the very first ML out, it will be disabled until all these 3 events happen again, which will bring us back into the initial state. So that's a cycle, right? So we got finite reachability graph over here, but we got infinite number of paths. Right? Again, reinforce what we said earlier. All right, let's now look at the state graph. Okay, right here. So the first thing for you to see is this. You can see here, this will be the pre-states for taking this action for ML out. After that one is taken, because now we talk about atomic updates, you can see both A and N are updated. So that's because we got a single label, right? That's exactly the point. So I'm going to say 1 here, and also the 1 here. So these are the atomic updates from ML out action. And since these two are done atomically, invariant 1,4 is not violated anymore. It's simply preserved, right? Invariant 1,4 is preserved, which is great. All right, that's the first point to illustrate. And the second point, starting from here, since the n here already reaches the maximum that we are setting, which is d equals 1. So that means ML out is going to be disabled. And how do we see that continue to be disabled? Exactly, that's something we also saw, something similar on Tuesday, actually. So you can see after we have done the ML out action over here, okay, let me just highlight it. After we have done the ML out action, I will go to here, and we reach the maximum for D, and then we go back to the choice. Let's say the non-deterministic choice actually happened to choose, it happened to choose the ML out, which are highlighted in yellow. Again, but it will simply go back to the loop. That means ML action is not happening anymore. So that means it's disabled at this point. Okay. So this part over here is really also very important for you to see. Right? So this part here tells you ML out action disabled until n is strictly less than the maximum. Right? That's important for you to see. And let's see exactly how that enabling is going to happen again, which I already illustrated to you, but let's see again. Right? It's very important. Remember, in the conceptual sketch, we are now in this state where ML out action is disabled. We will expect to see IL in, IL out, and ML in. After this particular sequence, we can see that we go back to this original state where n is strictly less than d. Right? Let's see exactly how that's going to happen. Right? So what you will see is, you can see, just follow this. You can see IL in action here, and then you will see also IL out action. Also, you will see ML in action. So that will be the sequence. Let me highlight the path. So the path that you're going to follow goes like this. I'll use in blue. What's going to happen is we're going to go here, 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 and then we got IL in. And then here, 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 and then we got IL out. And then we go here, 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 we got ML in. And after ML in action happened, you can see the green one here. This one here will go all the way back to the original states, like how we go back to the original state over here. So this is the place where ML action is enabled again, once more. Okay? This is important. So ML in action is enabled again because n is now again strictly less than d. Exercise that you may want to try is I'll write it down here, right? So we have, I think I've said everything I plan to say. So the exercise I'm going to write down here, you want to try. You want to generate the reachability graph or state graph with d is equal to 2. All right? And then you want to have the conceptual sketch. Of how ML out is enabled and disabled. And number 3, which is the most important one, but you need number 1 and 2 first, right? Number 3 will be you want to then inspect the reachability graph and verify that. So what can you verify? For example, you want to verify where can you see the pattern about the MLL being continually disabled. And then number two, how can you actually see the sequence of the other three events and eventually go back to the states where MLL is enabled again. So these are at least two things you can verify yourself on the diagram. All right? All right, any question? Yes, John.
So is the event guard evaluated on the transition between the states?
Okay. So the question was, when exactly was the event guard evaluated? I'll show you exactly. First of all, let's look at the module. Let's say, for example, here, if you look at the choice over here, right, that's a pattern that we have been learning. So exactly when will be, you can see, for example, let's say MLL. Let's look at that, since that's the event we're looking at. MLL is the label you can think about for the states where the PC counter is MLL. That would be the states right before this Boolean expression is evaluated. Okay? So what we can do is we can go to MLL. Okay? Let me show it to you. So let's say here, remember this is the pattern where we say MLL will be continually disabled. Right here, right? Let's look at that again. I'll also annotate. So if you look at, for example, MLL right here. When PC is exactly equal to MLL, you can think about, if you recall, the ML, let me use it a little bit thinner. If you, I'm going to copy again, copy a little bit from the module. That one there was MLL, and then we got some if condition here, and etc. Right? That's how it was set out in the module. Okay, so you can think about this state here is right before the if branch is evaluated. Okay, so this one tell you this is the states right before the guard of MLL is evaluated. Or you can think about this transition over here is to say, because we try to evaluate the guard for MLL, and that one should be false. Because it's false, it cannot be taken. So that's why we don't really take its action. We just go directly back to the loop. So you want to choose another event. It will just not be executed. Okay? So this one tells you the guard of MLL evaluated to false. So MLL action, which is the actual updates, does not happen, right? Right, John, does it help? Okay, good. Yeah, I think what John was just asking was very important. You want to see exactly what each state really means about a PC, right? So I think I will cover quite a bit today. All right, guys, any other questions about this? Yeah, explore really about these points very deeply. I think we still have time before your evaluation. So you can definitely take a look and let me know if you still got any struggle about understanding these. All right, if no further question, I think that's good for the second highlights for lab number 1. And let's now talk about the third one. Okay, the third one is going to be the system variance. Okay, that's something we're going to look at. Okay, the system variance. So I think the way it's going to go will be this. I'm just going to, rather than giving another mini lecture on the system variant from scratch, it may not be that good because you guys can already learn about it in 3342. So what I will do is I'll show you some annotated version of the notes. I will highlight the ones you need just to brush up very quickly or intuitively about the variance. So when I show you the module solution that you got for lab 1, you will see why things are done in that way. Well, I'll give you enough intuition. However, for those of you who want to recall the more details about variance, I will include certain parts of the lecture from 3342. You can also take a look, to brush up. That's something I need to rely on you. Right? But for today, I'll just give about 10 minutes maximum just to quickly recall what variant is about, 10 to 15 minutes. And then we'll look at the actual module solution for encoding the variants. I'll show you exactly how you should really go from the no variant version to the variant version. You will just have to introduce some extra variables and also some extra like an invariant check, right? It's something you've got to do. Okay, one thing at a time. All right, let's now do this. Let's now do this like a quick brush up, and then we'll take a short break, and then we'll take a look at the solution. Okay, that'll be the plan. All right, first of all, let's recall what lifelock really is, right? Lifelock, you should think of it similar to like a deadlock. Deadlock simply means your system is kind of locked in a very inactive manner. No event is being enabled, nothing can happen. Your system basically is dead. On the other hand, lifelock means your system is well alive. It's actually very busy working. However, what's really happening actively is not a good, it's not like a healthy pattern for your system. That's why we call it a lifelock. So the first point I would like to add over here is about the system, okay, about a lifelock. Lifelock simply means your system's progress is somehow locked, but in some active manner, in an active way. And what do we really mean by being active? Active in the sense that you have certain events diverging. Okay, and we also need to recall what diverging really means. So when we say events diverging, that means certain events simply they kind of happen to each other, well, like a sequence of events happening indefinitely. Other events simply just cannot happen anymore. Certain events happening indefinitely, which preventing others from happening. All right, so that's really just recall some definition about lifelock and also divergence for the events. All right, so these two are very quick recall. And then if we look at this model here, so we got ML, MLN, right? Just remember we got abstract model, we got concrete model, right? M0 and M1. So when we go from M0 to M1, M0 we only got two events, ML, MLN. For M1, we actually introduce ILN, ILout, right? So these are the new events. Normally, events will, divergence will only happen between the new events. Very quick recall about the details here. It is possible in the M1, if you have the new events, for example, let's say they're simply unguarded. They can just happen anytime. They're always enabled. Right? You can see I took out the guards for the two new events over here. They can always just happen. Okay? What's going to happen is in the M1, okay, so you can think about the concrete transition we are talking about over here is just M1. Whereas the abstract transition I'm talking about here is the M0, right? In your context for lab 1, M0, M1. So when I get, let's say in a concrete model M1, somehow after ML, after the car has already gone out, it is possible I may have indefinite interleaving between these two events indefinitely. They can just happen forever because they simply got no guard. They can just keep happening. And ML, MLN has no chance to ever happen again because these four simply just keep happening. And we said earlier, since these are the new events that do not really exist in the abstract world, in the M0. So one way to really represent them in the abstract model is we said they are simply like a skip, right? And skip in some way like a do nothing in the abstract model. So if we got the new events diverging in the concrete model, how would that correspond to what's going to be in the abstract model? It's almost like a BC looping, right? If you recall what you did in 2031, if you say while true and then simply do nothing, then your computer is really running, but somehow it's not really doing anything useful. So that's why divergence for the new event is bad. Right? There's a whole story that we spoke about in 3342, but for now, just very quick recall about divergence. All right? Any questions so far about divergence? All right? But for this course, if you ever got asked question about like a divergence, I'll be a little bit more explicit than in 3342. I'll tell you which events are the new events, so you can be more aware. So whenever you want to encode the variance for to really check for divergence, you always got to watch out, mainly for the new events. So that's something I will let you know explicitly. But you should also know how to encode the variance. Right, so I'm going to give you some reference about how this thing should be understood in more detail, but I just kind of captured the essence about it. Let me know. All right, that's one thing to remind. And then very quick comparison between invariance and also variant, right? Just to recall about the basics. So invariants, which we are still doing a lot for this course, they are simply Boolean expression that we want to check to make sure it's satisfied at every stage, right, in the model. On the other hand, variance is going to be some integer expression. That means in our encoding in TLA plus or in Pascal, we're going to introduce 2 rather than 1. That's the trick, which I'll talk about after break. The variant is going to be some integer expression that we're going to encode into our model and compare between the pre and post states. That's something we'll do. But conceptually, you want to think about the variant value is going to be like a natural number. It should never go below 0. It might reach 0, that's okay, but it should never go below 0. And if you ever try to plot the trend of the value for the variance, here is the rule. Okay? For any old events that already exist in the old model, in the abstract model, the variant value may either go up or it might just stay the same. And whenever you got any transition by the new events, it must be strictly going down. Right? We even got some proof obligation back in 3342. But in this course, you do not need to worry about those proof obligation. You don't need to. Okay? But you just need to know how to encode them in the Pascal. Right? So here I just read it to you. So each new event occurs. Each new event occurrence should strictly decrease the value for the system variance. That's something we will have to encode in our model and check it. All right, so this page here, just make sure to review about invariance, which should always be true. And for the variance, now you got 2 cases to check. Case number 1. Every O event is going to either increase or maintain the value for the variance. Case number 1. Every occurrence of the new events is going to strictly decrease the variant value. So these are the 2 cases, right, which you will see. Okay, 2 more. Okay, and this one here, just tracing. For your M1, you will see that the variant, also you will not be required to design a variant by yourself for this course. You don't need to worry. You'll always be given the variant to check. Okay. And for the variance, it's going to be 2 times A plus B. So this is like an integer expression. And that's something we want to observe. I'll give you some guidance about how to read this one here. Initially, after the initialization, this will be the post states. We got all the values for the variables being 0. After ML out, we only increment A, right? After incrementing A, you can see the variant value has become 2 times A, which would be 2 times 1, plus B. 0, we got 2, right? And etc. So you're going to kind of trace the value for the variance after each occurrence. If you plot the graph over here, what you will see is after the ML out, after each node events, it will simply increase the value for the variance. All right? You will see from 0 to 2 and 2 to 4. That's increment. But for every new events, let's say after ILN, after ILN, after IL out, after IL out, you will go from 4 to 3, 3 to 2, 2 to 1, and 1 to 0, strictly decreasing. One more. There is another O event, MLN. That one there, you can see 0 to 0 and 0 to 0 remain the same. Right? So that's the 2 cases I'm talking about. Okay, I'll highlight this, and then we're almost done. So think about here, 0 to 2 and 2 to 4, and also 0 to 0 and 0 to 0. So these are the two cases for the O events. So for the O events, the variance increase or stay the same. On the other hand, you can see here we got 4 to 3, 3 to 2, 2 to 1, 1 to 0, right? For all these. This one tells you for the new events, the variance value will just decrease, always strictly decreasing. Right? So these are the two cases. Right? You can see the plot. Yeah, the next page here, as I said, you don't really have to understand the proof obligation. I'm including that just for your reference, right? You don't need to do any proof for this course. But that one there, just want to show you. So we got two proof obligation, net and also var. Net is the variance should always be the natural number, larger than or equal to 0. That's something you will see in the actual module. Okay? And also the var over here tells you the variance in the post states for the new events must be strictly less than the variance value in the pre-states, all right, because it's decreasing. All right, and you don't need to worry about any detail. I just want to mention these two in case you want to recall, okay? All right, any question about, general question about variance? Of course, you gotta maybe look at the pages, look at the slides from before to recall the details, but that's a very quick recall. Any general clarification needed about variance? Okay, maybe study for that and let me know. Okay. Why don't we take a very short break, and after the break, we're gonna apply this kind of recall to the module. All right, so before the break, we kind of spoke about the very basics about variance. Please review the details. So these are only the pages you need to look at. And then, as I said, I will include a relevant lecture recording from the previous run for 3342. If you find the need, you can take a look, right? But what I'm going to show to you now will be something you definitely should know about encoding the variance, which you will not require to kind of encode in lab number 1. It will be too difficult at the time you're still learning about TLA+. But now that you already know about how to use the tool, now will be the time to know how to do it, okay? You can think about the way I'm going to present this is like this, okay? I'll show to you how you should look at. If you go back to the remote lab, let's say, remember we were looking at the bridge controller M1 no variance. Think about I'm taking a copy of this model here, and then I'm going to show to you exactly the addition you have to put into this one here. And the resulting extended version of the model is going to be the variant version, all right? So there's another file in your solution package. It's called bridge controller M1 variance. All right, that's the one. Another thing to mention, there is another file called bridge controller M2 no variance. So what I expect you guys to try as exercise will be create a duplicate of the M2 no variant version. And then try to see if you can apply what we learned about encoding the variance and do that one there by yourself and check it. All right, that will be a very nice practice. So for now, I'm just going to open the module and then show you something. So M1 variance. So that's the module we're going to look at. Okay, this one here. And then I'm going to go over with you, first of all, about all the additions you have to put in order to encode the variance, right? Based on what we said about before the break. Okay. Okay, give me one moment. Okay, let me just I'm going to highlight from scratch so you can see exactly the additions. Okay, just give me one moment. I'm just going to, yeah, there we go. All right. In total, there will be 1, 2, 3, 4. 4 variables you have to add, but they're kind of systematic, right? Let me start with the first two. Okay, let's talk about the variant value itself. As we said, variant itself is an integer expression, right? So what you will see will be, we're going to see this V, which stands for variance. So I call V in the pre-states and also V post in the post-states. What does that mean? So you can think about, we are thinking in this way conceptually. Given any arbitrary states, okay, any arbitrary states. And then you have some transition over here, right? And we got some event E. E here can either be a new event or it can be an old event. Depending on which category of event it is, the V change might be different, right? Okay. So here, so we got, let me write down here. If E is old, and also we got if E is new, right? I'm going to write it down in a moment. So you can think about the value for the variance in the pre-state is going to be V pre, and then V post. So that's the pre and that's the post. All right, let's now work out some conceptual sketch right away, right? So you will see that in the model. It will just be reflected faithfully. If the event is simply old, that means the value is going to increase or remain the same, right? How should we express that? Here we should say the V post and also the V pre. Now, what should be the relationship between them? If I say for the old events, it's going to either increase or stay the same. For example, just make some examples. So for example, let's say this. If the pre is 2, then it might be 2 or it might be 3. Right? So now what should be the formal relationship between the V post and V pre? So now what should I put here? Should I put less than or equal to? All right, guys, if you're still working on the logic, okay, maybe you take some time, all right? No, all right? The other way. V post is right here, larger than or equal to that. All right, don't memorize it, because if you memorize it, you're going to get confused during the test, right? You really got to understand what we're doing here, right? I'm going to show you the process of deriving it. It might be slow in the beginning, but that's okay. That means you really want to take some time thinking about it, all right? And then what about the new events? The new event, we know that it's going to decrease the value for the variance. So that means we're going to get the V post. It's decreased, so it should be strictly smaller. The V pre. All right, that's a conceptual sketch. And you will see that in the actual encoding. You can see between the V post and V pre, we consider all the possible relationship, larger than or equal to, and also less than, right? There's no other possibility. We're being very thorough about the relationship between the two values. All right, so let me change the color here. I really meant to put it in pink. So conceptually, we are really talking about the same variable, V and V. But in the pre-states, it will be some value. In the post-states, it will be another value. Okay, that's something we're going to do. Let's now just see where these two values will be used first, and then we'll talk about the other two variables. So the idea will be, you will see that, I'll let you follow the detail later. So there will be a label here, a single label. And for that particular label, you'll see there are 3 actions over here. So these 3 actions are going to be updated or going to be executed to do certain updates atomically. Atomic updates, right? We spoke about it earlier. And this one here, not surprising, we're simply saying V pre is this value over here, 2 times A plus B. All right? So if you look at the previous slide over here, you can see the variance that we're assuming is 2 times A plus B. Okay, we're just using it. Okay? And you will always be given what the variance should be. You don't need to come up with the variance yourself. Okay? So think about this one here is right before any events happen again. This one will capture the pre-state value of V, which is the variance for the next events. And when I say the next events, it could be an old event or it could be a new event. We don't know. But we want to capture its pre-state value first. Pretty much like over here, right? Capture its value first. What E exactly should be, we'll see. Old or new. All right, so this will be the only place where we're going to update or change the V pre-value every time right before we try to select some events for execution. Right, you can see it's right before the choice. Right, that's something you can see as well. Right before the choice. All right, and let's see about V post. So where should we update it? Conceptually, you should really update the post value for the you should really update the post value for the V after each event terminates, basically, after the action terminates. That's what you should do. Okay? To really do this atomically, unfortunately, you have to do it like this. Okay, I'll show to you. So basically, for every event action, you're actually going to update the V post. Okay, I'll show you exactly where. So in this case, we got, let's say, 1, 2, 3, 4. We got 4 events. ML out, ML in, IL in, IL out. So let's say for ML out. So you will see there's a label here. Let me use a different color. Okay, pink. Update event log ML out. There's one here. And then for next events, update events log ML in. That's the second one. Update event log IL in. That's the third one. And update event log IL out. That's the fourth one, right? So these are the 4 possible updates we have to do in order to update the post state value for the V, depending on which event it is. And for each one of them, you can see under that single label, part of it is about V post. V post over here. And then we got V post over here. We got V post over here. And then V post over here. Okay? So think about what's happening here. Okay? I'll do the conceptual sketch, for example. Let's say, for example, let's say if the V pre, let's say, for example, is equal to, it's 2 times A plus B, right? Let me just double check. 2 times A plus B. Let's say for that one there is 2 times A plus B. Let's say A there is simply 0, let's say. Okay? Let's say the action for the events itself is A plus 1, let's say. Okay? So what's going to happen is after the transition, after the action here, A value is going to be incremented from 0 to 1. And then we try to capture again the V post value right here. Okay? So in this post state here, the V post is going to be, again, 2 times A plus B, the same expression. But now, A has been updated based on the action here, A plus 1, right? 0 plus 1, which will be 1. Right? So the V pre over here is going to be, let's say B is also 0, right? Just to make it simple, let's say. So here, V pre will be 0. And V post over here will be 2, right? So you can see this value here will be 0, and this value here will be 2. And now if you compare the 2 over here, you will be able to see. For example, this one should be like an O event, right? Because you're strictly increasing the value. We want to make sure every time, if the E over here happens to be an O event, then it must be the case that this value here for the V post is strictly larger than the value for the V pre. That's something we're going to do systematically. So that's why you have to make sure the V pre is actually captured right before the event selection. And V post is also captured right after the action for each event. Right? Of course, you got to dive into detail to really see. But I think that's enough just for intuition. All right, so that's about these 2 variables. Now here, the only thing left, well, 2 things left. One thing is, how do we know whether E here is either an old event or new events, right? The way to tell is we need two Boolean flags to help us. Okay, I'll show it to you. So the two flags will be, let me just review it. Okay, since we talk about old and new, okay, right here. So we got old events occurred and also new event occur. Very straightforward, right? If the old event just occurred, like an ML out, you set the flag to be true. And if the new event, like ILN, just occurred, you set this flag to be true. And the idea would be, in the beginning, no event has occurred, so both are false. As soon as, for example, some old event occurred, this one will be true, and this one remains false, right? And similarly, if this one, new event just occurred, this one should be true, and this one should be false. There should be no states where both events occur should be true. And that one there, I also encoded as an invariant condition for us to check, right? That's something you can also look into, right? That's very important. Right, let's see where these two variables are updated. Very straightforward. So as I mentioned to you, in the actual test, I will let you know exactly which events are old events and which events are the new events. So you will know exactly how to set this flag. Okay? For example, let's say this. In the case of, let's say, ML out, we know that it's an old event. So that's why you're going to see that the old event flag is going to be set to true. And the new event flag is going to be set to false, right? Obviously. All right, so you can see that for these two variables here, especially this one here should be true, all right? And similarly, you want to look at, okay, this one here, this one here, this one here, this one here, and this one here, this one here. And the MLN is actually also old events, so we set old event flag to be true. And the IL out is ILN, IL out. They're both new events. So we're going to set basically the new event flag to be true, whereas the old event flag should be set back to false. Okay? And that's it. And notice the timing of setting this. The timing of setting this is right after the event action has been executed. You can see it's right after call the corresponding event, right after that. Okay? I'm going to write it down. So, for example, these three, they're on the same page, so I can do that. So you can think about it's updated right after the event action takes place. All right? That's about the coding part in the PlusCal. Right? Conceptually, it's not difficult. Just remember two things. Number one, you have to encode about the value for the variance pre and post. Number two, you have to encode about whether a new event occur or an old event occur. That'll be another two flags. And they got to make sure they put in the right place to update their value. Right? Study this coding very carefully. So that will be the encoding part. But now, how do we check it? Right? We have done so much scaffolding, so much hard work. But the value of doing these is we can check whether our system, whether it will have life lock. All right? Let's see how we can check it. And if you scroll down in the actual solution, of course, in this PDF over here, I simply omitted the translation part. But of course, in your actual TLA module, you would have done the translation. Okay? Let's see exactly. So you will see there is one section here about checking variance, right? Let's look at this section. That will be the one you want to look at. Other parts will be just like what you did in lab number one, right? Nothing special. You can take a look at them as well. So look at check variance. Okay. That's the part we want to look at them also very carefully to make sure you're okay with it. Okay, checking variance here. Okay, we got four things over here. So number one, over here, about this. 2 times A plus B. So this is the V that we have. And we say that it should be larger than or equal to 0. So this one just corresponds to the net proof obligation that we saw earlier, right? So we're basically saying that the V should be a member of the natural number. And this condition here should be checked as an invariance. What does that mean? That means for every reachable states for our state graph, the 2 times A plus B should always be a natural number. That's how we check the proof obligation in some way. All right? So this will be checked as an invariant. That's the first one. Okay, you can think about this is like the first one about the net. The next one there is not strictly part of the proof obligation, but I think it's also important to really make sure we didn't encode any mistake into our model. I'll show to you. Next one there, I call event log consistent. Remember, we got two flags. Either new events occur or the old event occur. We want to make sure there will be no scenario. Remember, that's the tilde here is the negation. There is no circumstances where the old event occur flag is true, and also the new event occur flag is true at the same time. If they are true at the same time, that means we have done something wrong, because each event is either old or new. Cannot be both. All right. So this one here, make sure an event is either old or new, not both. Right? This one is also very important, right? If you actually fail this check, that means you have done something very wrong with your encoding, right? All right, the next two. Okay, let's finish the next two. Oh, sorry. Beg your pardon. Okay, the next two. There we go. The next two will be the var proof obligation. Okay, two over here, separate. And this will be the var. And that one there really corresponds to the conceptual sketch that we did earlier, right? We said if the E here is old, then this will be the expression. And if the E here is new, then this will be the expression. Exactly that. Guys, what kind of logical operator should we do, right? You haven't seen the answer yet. How do we say that, right? Now we got the two Boolean flags already. And also we know that they cannot be true at the same time. And we also know, for example, when the new events occur flag is true, then condition number 2 should be the case. So now how do we put all these together into checks? Right? Too difficult? Eh?
Is it implication?
Sounds yeah, Farah, that's good implication. What exactly? Just give me some idea. What do you mean implication? Implication will be something implies something.
Yeah, old event implies that old event implies that the vpos should be larger or equal.
Yeah, as simple as that, exactly, right? And we know that the event that just executed is old if that flag is true. So if that flag is actually true, that implies this expression is true, right? Good, okay. That's exactly what you will see, right? Let's see that. So we got 2.1 over here, and also we got 2.2 over here, okay? And the end is going to be implication for both cases. You can see implication here. You can also see another implication over here. And we got two possible antecedents, right? Antecedent number 1, if the old event occurred. Antecedent number 2, then if the new event occurred. Right? If the old event occurred, we know that the value should be either increasing or stay the same. Right? Increasing or stay the same. And also, if the new event occurred, that means it should be strictly decreasing. Exactly that. All right? All right, a final thing I'll do for my part, right? The rest will be up to you. Okay, final thing. Okay. So if you go back to the the TLA plus. All right, so that will be the variant version, and then if you can click on the model, and here I simply try to devalue like a 5, but that's enough, right? That's enough car to really test. Okay, I set it to be 5, and you can see under the invariance, you can see all the conditions here I talk about, they're being checked, everything here. And then if I write a check over here, all right, everything checked. And we are talking about 552 states. All right. And normally, in this kind of case, if you actually choose to show the state graph, then it will show you that the graph is too large for you to load. So it really depends. Like if you set the D to be a little bit smaller, you might be able to see the graph, right? Just something practical for you to be aware. All right. Any question here? Okay, we spent, okay, question first, and then bear with me, 1 minute.
What is states found?
Hmm?
States found is actually larger than distinct states.
So let me get to that a little bit later. So that one is more about the states the algorithm actually have to visit, which will be a little bit different from how many distinct circles we have in the graph. That will be a little bit more details to do with the tool, which we don't have to worry. All right, guys, give me 20 seconds. So this lecture and last lecture, we really dive very deep into your lab number 1 solution. I think that's important. So I'm going to assume you guys are going to be fine. Look at the solution yourself and let me know if you've got any problems. And starting from next Tuesday, we'll do exercises on the math review, and then we'll move on to model checking lecture. All right? And for the lab tomorrow, come if you got questions. See you next week.